Hey, welcome. Did you know that every single second of your life, you're in the middle of an invisible battle? Seriously, pushes, pulls, cosmic tugs of war, they're dictating everything, from the way you walk to how the planets stay in orbit. So today we're going to pull back that curtain and make all those invisible forces, well, visible. Let's start with something super simple and see just how deep the rabbit hole goes.
So take a look at this. Seems pretty straightforward, right? A foot kicks a ball. But what's actually going on here? I mean, what sends that ball flying and what eventually makes it stop? To answer that, we've got to learn the language of motion itself.
And it all kicks off with one huge idea, the concept of a force. This is pretty much the bedrock of what physicists call dynamics, which is just a fancy way of saying the study of why stuff moves the way it does.
At its absolute core, a force is just a push or a pull. Simple. But the real magic is in that second part. It's the ability to cause a change in motion. And that means a force doesn't always have to make something move, especially if it's being canceled out by another force. You can think of it like potential just waiting to be unleashed.
And these forces, they come in two main flavors. First, you've got your contact forces, which are pretty much what they sound like. Things have to be physically touching. Think of friction between your shoes and the ground. And then you have the really mysterious ones, the field forces, that act across totally empty space, like gravity pulling you down to Earth right this very second.
Okay, so if these forces are all around us, but we can't see most of them, how in the world do we keep track of it all? Well, physicists came up with this brilliant tool for it. It's kind of like giving yourself physics X-ray vision.
I mean, how can we take this completely chaotic, invisible world of pushes and pulls and turn it into something clean, organized, and something we can actually understand? How do we draw a blueprint for what's really happening?
We do it with this, the free body diagram. And I'm not kidding, this is one of the most powerful tools in all of physics. What you do is you isolate one single object, just one, and then you draw out every single force acting on it using arrows. The way the arrow points shows you the direction of the push or pull, and how long the arrow is gives you an idea of how strong it is. It's basically a playbook for forces.
All right, let's actually try it out. Here's a classic physics problem. A block is just sitting on a ramp. It's not moving, just hanging out. Simple enough, right?
But now let's put on those physics X-ray goggles. What invisible forces are actually at play here? Because trust me, there is a battle happening to keep that block right where it is. So, what are the competing forces in this quiet little scene?
And boom, here's the answer. The free body diagram makes it all crystal clear. See, you've got gravity, which is always pulling the block straight down toward the center of the Earth. But the ramp is pushing back. That's called the normal force, and it's always at a right angle to the surface. And the hero of the story, the force that's winning the fight and stopping it from sliding, that's friction, pointing up the ramp, holding everything in place. Suddenly, the invisible becomes perfectly clear.
So, once we can actually see the forces, we need to know the rules they play by. And for that, we have to turn to the one and only Sir Isaac Newton. And these aren't just good ideas. They are the fundamental laws that govern motion everywhere in the entire universe.
Newton's first law is all about inertia. I like to call it the law of stubbornness. Basically, objects just want to keep doing whatever it is they're already doing. If they're sitting still, they want to stay still. If they're moving, they want to keep moving in the exact same way, unless some unbalanced force from the outside comes and messes things up. And that's all a net external force is, an overall push or pull that isn't being canceled out by something else.
Now listen up, because here's a little detail that trips a lot of people up. The law doesn't just say an object remains in motion. It says it remains at a constant velocity. That means the same speed and the same direction. So a car turning a corner, even if the speedometer doesn't change, is technically accelerating because its direction is changing. And that means there has to be a net force acting on it.
And this brings us to the big one, Newton's second law, F equals ma. This is the absolute engine of dynamics. It's the mathematical bridge that connects forces, an object's mass, and how its motion changes. So here's the profound truth it reveals about our universe. An unbalanced force is the cause, and acceleration is the direct effect. If the forces are unbalanced, the object must accelerate. Period.
Okay. So with Newton's rules in our back pocket, we can now take a closer look at some of the specific forces we deal with every single day, from the ground under our feet to the cables hanging over our heads.
Let's start with friction. You already know this one intuitively. If you've ever tried to push a really heavy sofa, you know that first shove is always the hardest. That's static friction. You have to overcome it just to get things started. This graph shows it perfectly.
See that huge initial peak in the force? Then, once the sofa is moving, the force you need to keep it going, that's kinetic friction, actually drops off.
All right, let's talk about that feeling you get in an elevator. When it first starts going up, you feel heavier for a split second, right? Well, that's not in your head. A bathroom scale actually measures the normal force, how hard the floor is pushing up on you. And to accelerate you upward, the floor has to push on you with more force than your own weight. So for that brief moment, the number on the scale literally goes up.
So what about tension? Well, tension is just the pulling force that exists inside a rope, or a cable, or a string. In this traffic light example, you've got gravity pulling the light down, and the two cables are pulling it up with a combined force of tension. And since the light isn't moving, we know for a fact that those upward tension forces are perfectly balancing the downward force of gravity.
Okay, now for the final piece of the puzzle. What happens when we have multiple objects all interacting with each other? We can't just look at one thing in isolation anymore. We have to look at the whole system.
Now, I know this might look a little complicated, but it's just the same rules we've been talking about, just applied on a bigger scale. We have one block on a table and another one hanging off the edge, and they're connected by a string. The fate of one is now tied directly to the fate of the other.
So the key here is to think of them as a single system. The weight of that hanging block is what provides the force to accelerate the entire system. That means both blocks together. The tension in the rope is what carries that force from one block to the other. They're a team now. They have to move as one.
Okay, you've learned about forces, free body diagrams, and systems. So to wrap this all up, let's apply everything we've learned to one final, kind of fascinating puzzle. We've got 3 identical jars. In jar A, there are 3 fireflies just hovering in the air. In jar B, there's just 1 firefly hovering. And in jar C, there's 1 firefly resting on the bottom. And now for the big question. If you were to put each of these jars on a super sensitive scale, how would their weights rank from heaviest to lightest? Think about it for a second. For a fly to just hover, it has to push air down with a force that's equal to its own weight. So, where does that downward push of air go? I'll leave you with that one to chew on. Thanks for joining me for this deep dive into the world of forces.